Hi and welcome to Assembly Language Programming. The first chapter we're going to look at here is digital logic. The reason we're looking at digital logic is that you really need to understand how a computer works, and in order to do that you really need to understand digital logic, because these are digital devices. And another reason you really need to understand these digital logic circuits is you'll see these circuits like this one up here in the documentation for the processors which you're trying to program in assembly language. And it's really important to understand what's happening by looking at these diagrams. If you don't understand the diagrams, it makes it really hard to understand from just the prose and the data books and the programming guides how things work. And so that's why we're looking at digital logic. I want to thank Mark Clement at Brigham Young University for most of this material. This is actually a link down here, this wiki, if you want to go looking at some more recommended reading. So what are our outcomes that we'd like to get out of this chapter? Hopefully you'll be able to understand how an inverter, an OR gate, an AND gate works, and how to make one out of transistors. Transistors are like little switches that are kind of remote controlled by their inputs. Hopefully you'll be able to convert logic to a truth table and vice versa. And you'll be able to use combinational logic to make any logical equation, and hopefully you'll be able to understand memory and using sequential logic, and also understand a finite state machine, and maybe even do something practical with that. So this first lecture is going to be on logic and arithmetic operations. The next one will be looking at logic devices, the transistor, how do you make AND gates, OR gates, NOR gates, and AND gates, and so on. And then the next section will be on logical equations and Boolean algebra, and then combinational logic devices. These are a little more complicated than just the simple AND and OR and so on, and inversion. And then we'll look at latches. Latches are another name for flip-flops, and they're really a basic memory element. And then we'll finally look at a finite state machine, and that's how a computer is actually made and what a computer is. So this will be our topics to cover in the logic area. So right now let's look at logical operations and logical arithmetic operations. So here's some logical operations. Basically, when we think about logical operations, we come up with a notation, and we use 0 to represent false and 1 to represent true. And so we will start with two different assumptions here, assumption A and assumption B, and then we can fill in these logical operations here. And not A is essentially whatever A is, but the opposite of that. So, you know, if A is false, then not A is true, and vice versa. And you can also think of that in terms of set theory. If this red box here is the universe and A is this circle, then not A would be everything but what's inside the circle. So then there's A or B. And if you look at this, if this circle was A and that circle was B, A or B would be this kind of binocular-like thing here. And you can see that up here on the truth table. If it's not in A and it's not in B, then it's not in A or B. But if it's not in A but it is in B, it is in A or B, and so on all the way down. So that's A or B. A nor B is actually just the opposite, or the not, of A or B. And then A and B means it has to be in A and in B to be true. So if you were here in A or here in B, you'd have to actually be in this little lens-shaped region to be in both A and B. And over here, if you're not in A and you're not in B, you're certainly not in A and B. And really the only way you can be in A and B is if you're in A and you're in B. So you can see how that kind of makes sense. And the A and B is just the not of that. And A XOR B, XOR is really a way of telling whether there's a difference between the two, A and B. And if there is no difference, then A XOR B is false. If there is a difference, it's true. So you can just see whether A and B are the same. If they're the same, you get a false, otherwise you get a true. And you can do these same kind of things with bitwise, bit by bit, as you see down here at the bottom. Okay, now arithmetic operations. And on the computer, we normally use a thing called 2's complement. It's actually wraparound. You put 0 kind of at the top of the circle, and this represents wraparound. As you go negative, you go in this direction. And we notice we go one more negative, then we can go positive, because when you look at the number of numbers you can represent by a bit pattern, it's going to be 2 to the n. And so if you look at, in this case, there's 16 numbers, and if you're going to include 0, you can only go to a +7 here. So when you add, you move in this direction. When you subtract, you move in that direction. And if you want to negate, you just go straight across. And you can do these kind of things in a bitwise fashion here. Check out these kind of things here. This number right here is actually -6. This is +7. If you add -6 to +7, you should get 1. And let's check it out. 0 plus 1 is 1. 1 plus 1 is, it's actually 2, but that's a 0 with a carry the 1. So I put a 1 here. That's also a 2, so I carry the 1. And that 1 is a 2, so I got a 0 here, and I'd carry the 1. But if you look at this, ignore that 1 that would have carried right out of the whole system here, since you've only got 4 bits, you've got a 1. So -6 plus 7 does indeed give you 1 here. So you can look at the other operations here too, and check them out. I suggest you do. This is the quiz. I would suggest you do this because my plan is in class, so we'll have first a little bit of time at the beginning of class for questions, but after that there will be a little quiz, and it will help you if you do the quizzes that are here in the slideshow. The slides should also be linked on the wiki, so you should be able to get this. These are Google Slides. You should be able to look at the Google Slides at your own leisure. So anyway, I hope that was helpful, and with that, we'll stop the recording for this one.